Okay, so today we have Hadi speaking. Hadi, do you want to give your own title?
Oh, yes. I think I titled this talk uh, A Character That Can Genuinely See uh, TMF. And by that I mean uh, uh, a character that can see into genuine TMF. And you can see more than just Borel equivariant TMF. Uh, uh, yeah, so very recently constructed last September uh, uh, a genuine equivariant refinement of TMF um, uh, that along the lines that the p torsion inside the elliptic curve uh, a formal neighborhood of that should be like the Borel equivariant thing, and the actual p torsion should be the genuine equivariant thing. So very constructed uh, genuine equivariant TMF, uh, and there were a lot of constructions that tried to do this, but now that there's a construction that does it once and for all, it's nice to have a character map that um, can see into, that can tell us a bit about it. So everything that I'm doing fits in the general framework of trying to find a geometric interpretation for TMF cohomology classes. And the way that this is done by Stolz and Teichner is the way they give a geometric interpretation for TMF cohomology classes is they find a geometric interpretation of K-theory, and they then relate K-theory to TMF. So they find a geometric interpretation of K-theory that readily generalizes to higher height cohomology theories. And in this case, Stolz and Teichner, they give it interpretation of K-theory in terms of field theories, and then that field theoretic description of K-theory generalizes to TMF. Now, what they do is a conjecture, and we want to try to replicate their strategy. So K-theory, these are vector bundles, the group completion of the monoid of vector bundles. Vector bundles is a perfectly fine geometric interpretation of K-theory, but it doesn't readily generalize. There isn't an easy notion of a higher vector bundle, although I have spent time thinking about that. Instead, one focuses on the K-theory of BG, and these can be understood using representations. This is the representation ring of G. And there's a map from here to here from the group completion of all the representations of G. That's a representation, and you can get a K-theory class by taking B's of both sides.
Sorry, it doesn't matter at this point, but you consider it complex representation here.
Yeah, complex representations.
And this is during all your talk.
Yeah, no, but you raise an interesting point. When you're taking complex representations versus real representations, like that sort of amounts to taking like a functor of points valued on a different ring. In this case, the complex numbers versus the real numbers. Maybe I'll say more about that in a second. So this thing over here is a vector bundle. Now, what did I do? I wrote, I tried to understand the K-theory of BG using representations. Now, representations themselves also don't really have a nice generalization to higher height cohomology theories. But class functions, the notion of a class function does have a generalization that's very easy to higher height cohomology theories. So that's the direction that I'm going in. I'm going to try to write down the K-theory of BG using class functions, and then I'm going to try to generalize that to higher height cohomology theories. Let me focus on the group Z mod 2 because it says a lot already. The representation ring of Z mod 2 is equal to, it's generated by the character e to the 2 pi I over 2x. So the square of that character is 1. And there is a map from the representation ring to the K-theory of BZ mod 2. And this character, e to the 2 pi I x over 2, this is sent to the tautological line bundle over BZ mod 2. Now, one thing. Usually people want the generator to be in degree 0. So people take the generator to be the tautological line bundle minus 1. And that satisfies that the property that the tensor squared equals 1. Now, K-theory is vector bundles over a finite CW complex. But in order to get a cohomology theory, what you do is that you say that the K-theory of a space is the vector bundles over that space if you're dealing with a finite CW complex. And you define it for arbitrary CW complexes by taking limits with colimits or something. Limits. So this actually needs the double adjoint over here. These are the K-theory of BZ mod 2 is power series in X modulo X plus 1 squared minus 1. Now, notice that this is, to get from here to here is just a completion. To make this explicit, I'm going to write this down as zx modulo x plus 1 squared minus 1. And this map over here is an iso after I complete at the ideal generated by x. So this is completion at x. And it's nice to know that this is the ideal generated by x is the ideal of dimension 0 vector bundles. So that's what this thing is geometrically. So when you complete at the ideal generated by dimension 0 vector bundles, you get an isomorphism from the representation ring to K theory. Now, I'm trying to write this down as, I'm trying to write down the K theory of BZ mod 2 in terms of class functions. So let me do that. So the representation ring was this. X squared, this is equal to x squared plus 2x. And if I want to get class functions, I can use the Chinese remainder theorem and get a map to z plus z. This is the map, and in order to make it an isomorphism, I need to invert the prime 2. So once I do this, I get class functions. On z mod 2 valued in z 1/2. Right. And these are just functions, but they're also class functions. Now I want to do the same thing for K theory. K theory was z double adjoint x mod x squared plus 2x. This also has a map to z plus, it's not going to be a z over here, it's going to be a z mod 2. Sorry, the two adducts. Where did the two adducts come from? This x squared plus 2x tells us that x squared equals minus 2x, and x to the n equals negative 2 to the n minus 1 x. So this power series in x turns into power series in 2, and that's where this 2ix factor comes from. And just as over here, in order to make this an isomorphism, I need to tensor with z 1/2. this is then an isomorphism. So these are now class functions on, well, I want to get class functions on Z mod 2. So I need to do a completion at the ideal of dimension 0 vector bundles to get from here to here. Now, here's the problem. I'm trying to write down a description of K-theory that generalizes easily to higher height cohomology theories. And so I can't have in the description of this completion that I'm completing at the ideal generated by dimension 0 vector bundles. I can't do that because vector bundles don't have a nice generalization, nice easy generalization to higher heights. So instead of completing at the ideal of dimension 0 vector bundles, this computation suggests that I instead complete at the ideal generated by 2. So I complete first, and then I take invert 2. And then I get an isomorphism. So sum this up, I get a geo interpretation of K-theory as class functions. If I complete at 2, the significance of 2 is that 2 is the order of the group over here. And I invert 2.
What's geometric about class functions?
Well, it's the best it's sort of like the best thing that we have. So we can't have vector bundles because vector bundles don't generalize best nicely to higher height cohomology theories. Because then we say, okay, let's look at representations. Well, those don't really. The notion of a higher representation is also hard. So class functions are sort of the next best thing, because class functions do at least generalize. They're a little less they're a little bit less geometric than the notion of representation, but at least they generalize to higher heights. Well, I guess one thing is nice. If you're dealing with an abelian group, then these class functions, these are just functions. So like these are sort of like functions on these are functions on Z mod 2, and Z mod 2 is like the 2 torsion inside over here, the multiplicative group. Yeah, so this map over here, once I tensor properly with, once I base change to this ring, what I'm doing is that I'm looking at functions on Z mod 2 to functions on the 2 torsion inside S1 to form a neighborhood of functions on the 2 torsion in S1. And I'm taking a formal neighborhood because I'm looking at a neighborhood of the identity. So there's that nice geometric picture when I look at class functions. Yeah, so it's the thing that's the most related. It's the thing it's related to representations, and it generalizes nicely to higher heights. Okay. Now, I just want to tell you briefly about how the notion of a class function generalizes to higher heights. I wrote it out because I didn't want to spend too much time on it, but a class function is the same thing as functions on conjugacy classes of G. And conjugacy classes of G can be thought of as conjugacy classes in the action groupoid of G acting on G. And the action groupoid of G acting on G can be thought of as a sort of loop space, functors from the one object category with p-adics orthomorphisms into BG. So functions on isomorphism classes of this groupoid of functors from this category into from S1 into BG, that's sort of like the same thing as a class function. But if I want to generalize this to higher heights, what ends up happening is that a higher height class function is just like the n-fold loop space of BG. Now, this is one way of looking at it, but one.
Sorry, I still do not understand the first line in your list in the slide. So you're saying that class function is a function from action groupoid of periodic numbers to action groupoid of G, acting on.
Yeah, I'm saying that a class function is, yeah. And G is a finite group over here.
The class function is a function on this space, not on.
It's a function on the isomorphism classes of the groupoid. Now, I think this is a bit confusing. The notion of a higher order class function, I think it comes out much more naturally when I look at an example. When I look at an example of
No. Forget for a moment higher class function.
Okay, sure.
Your usual notion of a class function.
Okay, sure.
So class function is a function on conjugacy classes of your group. Or on the conjugacy classes of a so you're interested only in like a cyclic group of order P, where.
Sure. Well, I guess yeah. I'm interested mainly in finite groups.
Yeah, you're interested in finite groups, but you're also interested on.
Yeah, just at the prime P. Yeah.
Also interested only in elements of P torsion.
Yeah, P torsion. Yes.
And you're saying that a class function is a function on a such set of functions from this action groupoid to this action groupoid.
Yeah, from point mod, from this is sort of like an S1.
No. So
I can actually take out this P over here. Is a bit confusing. I can take that out.
I also think that it's not a periodic numbers. It's like mu P infinity. It's like.
Yeah. So let's take out that P over there. That I might have been an error. So if we look at point mod Z, so functions from point mod Z into point mod G.
So this is the same as a homotopy classes from BZ to BG, and this is the same as a conjugacy classes in pi1 of BG So this is the same. Oh, this is the same as a conjugacy class in G.
You can think about it this way, but I think an easier way of thinking about it is that the functors from here to here are determined by where it sends a generator of Z. Uh, a generator of Z will be sent to an element G inside the group. So that's going to be an object inside this category. And a morphism is going to be a commutative diagram, and that's going to correspond to conjugation by G.
No, I understand. You can say what action required for Z, it's the same as a S1, and action required for G, you can think about as BG. And what you have done is the homotopy classes from S1 to BG.
Yeah.
And precisely conjugacy classes of the group G.
Yeah.
Okay, I see. Okay, and now you simply put the not S1 but a torus of dimension.
Yeah. So that's going to correspond to like taking an n-fold loop space. You take like an n-fold. Yeah.
Yeah, sure. Mm-hmm. Yeah, and I'm also was confused about periodic numbers here. I thought it has.
Yeah, I shouldn't have put it there. It just.
No. I thought it. If you insist only in torsion elements, you have to take a colimit of.
Yeah, I should have written down Z mod P infinity instead of.
Yeah, exactly. Yeah. Mm-hmm. Okay, good. Thanks.
Okay, so maybe I shouldn't have used this. Well, whatever. It's nice. I like it. But a much easier way of seeing how n class functions are, seeing what the generalization of a class function to higher heights is, will come out of an example that I'll do shortly. Okay. So that was the generalization to higher class functions I wanted to mention, just to tell you that it's there. And the other thing I wanted to do is I wanted to tell you how the theorem generalizes to other groups. So this is a theorem. So what I wrote down was that to complete at the prime P, the way that Z mod 2 generalizes is that if I look at Z mod P to the R,
So if you with subindex P subscript.
I mean, so I can define P complete K theory
Okay,
by
fine. Okay.
by I tensor I complete the K theory of X at the prime P for finite complexes, and then I define it for arbitrary CW complexes by taking limits.
Yeah. Okay. Fine. Mm-hmm.
So I wanted to complete at the prime P to get these isomorphisms to have over here, and I want my evaluation maps that I had in the Chinese remainder theorem to be there. So I adjoin the roots unity. And I want the Chinese remainder theorem to be an isomorphism. So I invert the prime P. Or I guess, yeah, I invert the prime P. And if I look at there's theorem is that this is isomorphic to class functions on Z mod P to the R valued in this same ring. And this theorem works just the same for abelian groups because I can take products of z mod p to the r's. And if I look at induced representation, I get my theorem for K theory. If G is has p power elements, then p complete K theory of BG tensor map from here into class functions of on G valued in P to the R through unity. This is an isomorphism. Okay, so I think that was a lot. I just do not use right now. So here's the monkey break. Any questions?
Should that be 1 over p to the r at the end?
Yeah, inverting 1 over p to the r is the same thing as inverting 1 over p. Let me just be consistent and just invert 1 over p each time. Yeah, so this is character theory for K theory.
Hari, could you explain why, like, all we're doing is looking at the K theory of BG. So why should we expect this to kind of help with understanding, like, just cohomology theories of an arbitrary space that isn't like a BG?
Oh, yeah, that's a good question. So this generalization of a class function over here, this actually generalizes to it generalizes to any orbifold. A class function on an orbifold X is the same thing as, well, I take conjugacy classes of X, cis functors, from point mod Z into X. It's my orbifold X. So that's, and I take isomorphism classes of these. And I take functions on these. And higher order class functions on X are the same thing as functions on iso classes of functors from point mod z to the n into x. So the notion of a class function generalizes to higher heights and to orbifolds, and this all works. This also can be used to say what a class function is for what is known as a pi finite space. So here, my orbifold over here, I wanted it to have finite stabilizers. So I wanted to be able to form like point mod G, where G is a finite group, or I want stabilizer at every point in the orbifold to be a finite group. Having finite stabilizers is what allows this description, because I need to send a generator of 1 to something. So if I have a orbifold with finite stabilizers, then n-class functions generalizes, and class functions generalize to orbifolds. And if I have a pi finite space, a space with like, I forget the exact definition of it, but I think it's just that like finite homotype groups or finite pi one, something like that. I forget the definition of a pi finite space, but
I think it's finitely many non-trivial, and they're all finite.
Yeah. Okay. So this framework generalizes to pi finite spaces.
Okay.
And so part of the things I want to do with this eventually is I got interested in this because I was interested in higher vector bundles, and I wanted to be able to use this to say what higher vector bundles tell us about genuine equivariant TMF. That's one thing I want to do. So I hope to use this to help me do that. Yeah, so there is a notion of a higher vector bundle, and it's just a bit difficult because it's not clear what it is. But yeah, I hope to use this to say what higher vector bundles tell us about equivariant TMF.
Is your higher vector bundle like an element of like the 2 vector space category?
Yeah, so it's like a parameterized version of 2 categorical vector spaces. Yeah, and conjecturally, 2 vector bundles are the same thing as the K theory of KU, and people thought that the K theory of KU was like equal to TNF, but nobody thinks that anymore. And so now people just wonder what the hell 2 vector bundles tell us about TMF. So yeah, that's something I hope to do.
I also want to remind you the current definition of a higher vector bundle is very awful, so it's better to avoid it.
Yeah, it is very awful because there are a bunch of different there are many candidates for what the right definition of a higher vector bundle is, and there's no real clean definition of what it is.
Yeah.
I don't really have it off the top of my head. I'm sorry. I'd have that. Maybe in tea time I can tell. Maybe something. I think like there's supposed to be like vector bundles with coefficients in KU or something, if I remember right. Okay. Vector bundles with coefficients and vector bundles with some. Like a gerb is an example of a higher vector bundle. So they're kind of geometric. Okay. I should go on if I don't want to run out of time. Okay, so let's look at higher head cohomology theories. So if I'm looking at a complex-oriented cohomology theory, and I want the assumption that it's P-complete. Now, I'm going to look at just the zeroth cohomology because that's something that you can do with complex-oriented cohomology theories. All the information is concentrated in degree 0, and I want the P completion of this to be the cohomology theory, the 0th degree cohomology. And if you have a complex-oriented cohomology theory, then the cohomology of BS1 is equal to.
Harry, are you P-completing the group or P-completing the spectrum?
The spectrum.
I see.
And if I look at the multiplication by P-map,
Is E have to be connective here?
I'm not sure, I'm sorry.
What does E0 mean, the 0th homology of a point?
Yeah.
Well, so normally wouldn't you have the negative homotopy groups of E coming in?
Yeah, I don't remember exactly how, for complex-oriented cohomology theories, one reduces to degree 0. It's been a while since I looked at it.
It should be like power series where like the term and the gradient of the like element of the homotopy group and the gradient of X like to the n add to 0, I think.
Yeah, so maybe I'm looking at a connective spectrum then. So the cohomology of the multiplication by P-map this map turns into a map from the power series ring to the power series ring. And it's summed to some power series. It's summed to some power series, which I call the P series of X. And the P series of X can be factored as a polynomial times a unit and this polynomial it's a degree p to the n poly. And this n over here is called the height of E. So that's what the height of a cohomology, of a complex-oriented cohomology theory is. It's just the degree of the polynomial that comes out. So for instance, when I look at K theory, the K theory of let me say this first, actually. So when I look at the cohomology of B Z mod P, I want to replicate the calculation I did with K theory. This is equal to the cohomology of VS1 modulo the multiplication by P map using the stereospectral sequence. And this is E naught double adjoint X modulo the P series in X. And this can be further simplified to E naught double adjoint X modulo a polynomial f of X. So in the case of K theory,
do we also assume that your cohomology theory is constrained only in even degrees?
even periodic.
Not just even periodic, no, you constrained in even degrees.
Yeah.
Because you want exact sequence here, yeah. When you can compute E0 or BZ mod P.
I don't think you don't need in order to make the stereospectral sequence work. You don't need it to be concentrated in even degrees, so that can be.
No. You have something like a Gisin spectral sequence, Gisin exact sequence where.
Yeah, you do, but you don't. Having it concentrated in even degrees simplifies the calculation, but it's not necessary.
Okay, fine. Yeah. Okay.
So I also have a question.
Yeah.
I thought the degree of X for these complex-oriented theories was degree 2, right? It's coming from CP infinity. So don't you need negative homotopy groups to get a non-trivial polynomial, since the map needs to preserve degree?
Don't.
Right. I mean, isn't the reason that this works for K theory is because K theory has Z's in every even negative degree, so an element of Z can be conserved with arbitrary negative degree. Or am I missing something?
You can choose like the degree your generator's in. Like normally it lives in degree 2, but if I just multiply it by something in degree -2, I have something in degree 0, and you can treat that as your generator.
Right, but if it's a connective theory,
Yeah.
then the only thing you have there is 0.
Yeah, maybe there's a problem here.
I think the assumption is what is connective is redundant here.
Okay.
So you want something like a usual complex K theory. It's not connective.
Yeah, it's not. Yeah. And I guess under some assumptions, I should be able to write down that the cohomology of BZ mod P is E naught double adjoint X modulo some polynomial. And I got this polynomial, I got this factorization of this using the Weierstrass preparation theorem. So I guess I want whatever assumptions I need to make that work. Now, to replicate I want to replicate what I did with the Chinese remainder theorem over here. I want to replicate this for this E star double adjoint X mod P of X. So in order to do that, I pick a field with make it algebraically closed. That's going to let the evaluation maps in the Chinese remainder theorem exist. And I'm going to make it be a field. And what that's going to do is that's going to make the Chinese remainder theorem map an isomorphism. If I do that, then my claim is that E star E naught double adjoint X modulo PX tensor K. This will be functions on Z mod P to the N valued in K. So this map over here is the Chinese remainder theorem. Now what I need is that I want that P of X has P to the N different places to evaluate it at. And I want them to be distinct in K. So in order to make sense of a root, I need K to be I need K to have a topology, and so that's going to be solved by making K an E naught algebra.
So probably it's function not valid in K, but something like E0 tensor K.
Stefan?
K is algebraic closed field, and which is also E0 algebra.
Yeah.
So E0 embedded where? Okay.
Yeah. So K has a topology to make sense of roots inside K. Now it has P to the N roots because this is equal to f of X times a unit. So that's going to imply that they're P to the N roots because f of X has degree P to the N. Now, they're distinct inside K because there is a logarithm of P f of X. There's a logarithm of the P series such that this is equal to P times the logarithm of X. So the logarithms has its coefficients. The coefficients of the logarithm will exist inside K. And this is going to imply that P prime of X is not equal to 0. To imply that there are no multiple roots.
So K not just the algebraic closed field, it's a closed field of characteristic 0.
Yeah. Yeah, I think you don't Yeah, it's close to characteristic 0. I think somehow you get that from being E-not algebra.
Probably, I don't know.
Yeah. I think because K is a characteristic 0 because you're
So
E-not algebra.
U0 has no P torsion.
No, it's like something like the p-adics. It's not like C mod P.
P torsion is P complete.
P complete, yeah.
Okay, fine.
And then Hadi, are you about good to wrap up soon-ish?
Yep.
Okay, perfect.
So the theorem of Hopkins-Kuhn-Ravenel the theorem of Hopkins-Kuhn-Ravenel well, actually, let me do an example of the theorem first. So this is what we just proved. We just proved that E naught of BZ mod P tensor K is equal to functions on Z mod P to the N valued in L. Valued in K. When K is an algebraic closed field, that's an algebra. And the actual theorem of Hopkins-Kuhn-Ravenel says that E naught of BG tensor over E naught with L equals functions on G to the N modulo the conjugation action valued in sorry, this is a K. Now, a couple things that Hopkins-Kuhn-Ravenel do is that, so over here, G is equal to P to the R to find a group. A couple things that Hopkins-Kuhn-Ravenel do is that they ask what's the best choice of the ring that I need to tensor by in order to get class functions. And another thing they do is that by a silly trick, you can generalize this to groups that are not of order P to the R. You replace functions on G to the N modulo the conjugation action. You replace that by functions on N commuting elements of order of P torsion valued inside K. And there are generalizations of this to orbifolds. The thing that I'm most interested in is, well, a lot of what is done in over here, it works perfectly fine if instead of looking at E star BG, E star B Z mod P, that is the P torsion in the formal group, I look at the P torsion in the group associated to the cohomology theory. And one nice thing that I stumbled upon was that there is a character map that goes from Tate K theory to the Z mod P equivariant uh, version of Tate K theory to two characters, but Tate K theory is a height 1 cohomology theory. So the fact that it goes to two characters instead of one characters, two characters are functions on Z mod P to the 2. The fact that it goes to two characters instead of one characters shows that it sees some of the genuine equivariant information inside Tate K theory. Yeah, I think I'll stop there.
Great, thank you, Hadi. Any questions for Hadi?
I have a question as usual. So, where exists such homology theory as a morality theory, and you even can consider it as a even periodic. And it is also a complex-oriented theory.
Yeah.
Does this theorem applies for morality theory?
Yeah, that's the main
so your field here will be some field of prime characteristic.
Yeah. Morality theory is like a P-complete theory. So like it's like these zeroth cohomology of a point is P-complete. It's torsion free.
It's not torsion free.
Yeah, it is.
K theory, not E theory.
Oh yeah. Oh, sorry, yeah. Yeah. So I guess I want it. Oh yeah.
It still will be applicable. Or you get some. Yeah, I mean you can use here. Okay, probably it's a problem of proof. Or what you just said. No, okay, that's probably it's still applicable here. And there exists some generalization not for BG, for description of BG, but some higher Ehrenberg-MacLean spaces or in this setting. Because
is there a generalization to pi finite spaces?
No, not for pi. No, okay,
to Ehrenberg-MacLean spaces.
At least for Ehrenberg-MacLean spaces. Because because K theory of Ehrenberg-MacLean spaces, morality theory of Ehrenberg-MacLean spaces.
Well, yeah. So I guess like if you take like instead of BG, you take like B to the NG, then you would think that maybe that could be undone by taking like n-fold loops, and like so.
I mean, it's computed. Morality theory of Ehrenberg-MacLean spaces, but probably there exists some description which looks like this one.
Yeah, I'm thinking that maybe like these like n-class functions that corresponds to like taking like n-fold loops, like maybe that could like undo like the B to the NG when like that's present in the Ehrenberg-MacLean spaces. I'm just thinking roughly, maybe, perhaps, maybe.
Yeah, okay, it's fine, yeah.
Any other questions? Okay, I'll go ahead and stop the recording.